Imagine the shortest possible moment, not a second, a millisecond, or even a trillionth of a second. Something far smaller. So small that time itself might stop making sense. Physics suggests such a limit exists. It's called Planck Time, and it's unbelievably small, about 5.39 times 10 to the negative 44 seconds. If 1 second were stretched to the age of the universe, a Planck time would still be unimaginably tiny. But here's the strange part. According to modern physics, nothing meaningful can happen faster than this. Not because our clocks aren't precise enough, but because time itself may not exist below this scale. So the real question is this: what happens when we push time all the way to its limit? What happens at the edge of time? Most of us think we understand time. Clocks tick, seconds pass, events happen one after another, but physics reveals something strange. Time isn't universal. According to Albert Einstein's theory of general relativity, time can stretch, compress, and slow down. Two observers can experience time at different rates. Near a massive object, time slows. Near something extreme like a black hole, this effect becomes dramatic. To someone far away, an astronaut falling toward a black hole appears to slow down. More and more, until they seem almost frozen. Time for them still passes normally, but to the outside universe, their clock nearly stops. Time is flexible. It bends, it stretches, it's woven into space-time itself. But here's the deeper question. Is space-time infinitely smooth, or does it have a smallest possible unit, just like matter is made of atoms? Could time be made of tiny, indivisible moments? Moments that cannot be divided further? To understand that possibility, we have to go deeper than atoms, deeper than protons, deeper even than quarks. At the smallest scales physicists know, reality begins to look strange. There is a length called the Planck length, about 1.6 times 10 to the negative 35 meters. To give you a sense of scale, if an atom were the size of the observable universe, the Planck length would be roughly the size of a tree. It's almost inconceivably small. And if you ask how long it takes light to travel that distance, you get the Planck time. Some physicists suspect this might represent the smallest tick of reality itself, like the frame rate of the universe. If that's true, the universe would update about 10 to the 43 times per second. 43 trillion frames every second. But whether reality truly works like that is still unknown. Here's where physics runs into trouble. Our two best theories of reality are incredibly successful. One describes gravity and the structure of space-time. That's general relativity. The other describes the behavior of particles and energy at the smallest scales. That's quantum mechanics. Both theories work astonishingly well. They've predicted countless experiments correctly. But when you try to combine them, they break. The equations explode into infinities, and infinities in physics usually mean one thing: the theory has stopped working. This breakdown happens precisely at the Planck scale, at distances near the Planck length, at times near the Planck time, which means the edge of time isn't just small, it's where our understanding of physics collapses. To see why this matters, let's rewind the universe, back past galaxies, stars, atoms, back to the very beginning. For a long time, physicists believed the universe began as a singularity, an infinitely dense point, a moment when the universe was infinitely small and infinitely hot. But there's a problem with infinities. They usually mean the theory is incomplete. When we rewind the equations of the universe, something strange happens. The laws of physics stop working before we reach the beginning. Specifically, about 1 Planck time after the beginning. Before that moment, our equations simply fail. We don't know what the universe looked like. We don't even know if the word before makes sense. This earliest era is called the Planck Epoch. It lasted less than 1 Planck time, and during that tiny moment, the universe was unimaginably extreme. Temperatures may have reached 10 to the 32 Kelvin. That's 100 billion trillion degrees. At those energies, the four fundamental forces may have been unified. Gravity, electromagnetism, the strong nuclear force, the weak nuclear force, all part of a single force. Space itself may not have behaved like space. Time may not have behaved like time. Instead, reality might have resembled something far stranger, a chaotic storm of quantum fluctuations. Physicist John Archibald Wheeler described this idea as quantum foam. At incredibly small scales, spacetime might not be smooth. Instead, it could behave like a turbulent ocean, distances constantly fluctuating, tiny wormholes appearing and disappearing, space folding in on itself, time wobbling unpredictably. If you zoomed in far enough, reality might look less like a calm surface and more like boiling water. And here's the strange consequence. Trying to measure time intervals smaller than the Planck time may require so much energy that the energy itself would collapse into a black hole, meaning the act of measuring smaller time intervals would destroy the measurement. Nature may literally forbid us from probing smaller moments. So what happens beyond the Planck time? Possibly nothing. Not because nothing exists, but because time itself stops being a useful concept. Some physicists suspect time might not be fundamental. It might be something that emerges from deeper processes. Think about temperature. Temperature seems real, but a single molecule doesn't have a temperature. Temperature only appears when many molecules interact. Time might work the same way. At large scales, time flows smoothly, but at the smallest scales, the concept may dissolve. Events might not have a definite order. Cause and effect might blur. The distinction between past and future might disappear. There's another possibility. Maybe time really does come in discrete chunks. Some theories, like loop quantum gravity, suggest space-time might be made of tiny building blocks, little loops woven together. In that picture, space is granular. Time advances step by step, like frames in a film. If that's true, the universe could have a maximum refresh rate. Reality might literally update itself once every Planck time. But experiments so far haven't confirmed this. Space-time still appears continuous, which means the true nature of time remains one of physics' deepest mysteries. Now consider another puzzle. Why does time move forward? In most physical laws, time works just as well backward as forward. Yet in everyday life, time has a direction. We remember the past. We don't remember the future. This direction is called the arrow of time, and it's linked to entropy, the tendency for disorder to increase. But near the beginning of the universe, entropy was incredibly low, which means the arrow of time may have emerged gradually. Time might not even have had a direction during the earliest moments. At the Planck scale, the distinction between past and future might not exist. Now jump far into the future. Trillions of years from now, stars burn out, galaxies fade, black holes slowly evaporate. The universe approaches what physicists call the heat death of the universe, a state of maximum entropy. Nothing happens anymore. No stars, no structure, no energy gradients, just a thin, cold fog of particles. Time still technically passes, but without events, the concept of time becomes meaningless again. In a strange way, the universe might have two edges of time, at the beginning and at the end. Both extremes share something remarkable. Structure disappears, physics becomes strange, and time itself loses meaning, which raises a profound possibility. Maybe time only exists in the middle of the universe's history, right now. Right where we happen to live. Maybe the past and future edges of the universe are timeless, and the flow of time we experience is just a temporary feature of cosmic progression. The Planck time marks a boundary, not necessarily a physical barrier, but the edge of what our theories can describe. Beyond that boundary, our equations fail, our models collapse, reality becomes unknown. And yet, physics has reached edges like this before. Every time we've hit a wall, a deeper theory eventually appeared. Newton's physics gave way to relativity. Classical physics gave way to quantum mechanics. And someday, A new theory of quantum gravity might finally explain what lies beyond the edge of time. Maybe time is an illusion. Maybe the universe is fundamentally timeless. Or maybe reality is far stranger than anything we've imagined. What really happens at the edge of time?